Hello everyone, welcome to the presentation about SQL and NoSQL Symbiosis, how we can see it in Avast software. My name is Pavel Kučera, and together with Jonathan and Zbigněk, we would like to present you some use case, how we deal with kind of complex data store. On the right side of this slide, you can see is the final diagram of the Symbiosis, and we will go through the description of the service, go inside the data analysis, different database architecture, and we should end up with the final implementation and deployment. Let's get started. Avast Software is the creator of the most spread antivirus solution in the world. We have more than 160 million of users. That's why we are facing heavy load on our backend services, and we need to think, in how to do them, pretty well responding and handling tons of requests a second. We found out that the understanding of the distribution of the executable files around the world is kind of important for antivirus analysis. So, for example, we would like to know how many users owns the particular executable file. Also, the other statistics or important data is when the file was first seen. This is the reason why we introduced file reputation service. So how does this service work? We store the information about the executable files we saw on our clients around the world. Can anyone guess how many executable files we saw in last couple of months around the world? Any guess?
10 million.
Okay, 10 millions. Another guess? 10 billion. The answer is in the middle. We saw 1 billion. Yeah, but we have T-shirts for you both. So the key for us is the SHA hash. So through this key, we can identify any executable file in the world. Yeah. So this would be our key in our database solution. So we had been facing a couple of challenges. So as mentioned, we need to be able to store more than 1 billion file information. Also, we need to respond 100,000 requests a second, be very fast in response, so the user is not bored because of waiting before the file execution. And finally, be able to respond with the accurate data. 10 seconds, old data should be enough for us. So this was kind of the requirements from our Virus Lab team. So it looked that we should probably use disk storage for persistency on large volumes. The application should run on more nodes, be hosted on different locations, and these locations need to be synchronized quickly. we could not suit the optimized solution without more understanding the data. We had been expecting something like what's described on the picture. Yeah? On the x-axis, there is number of file owners, and the y-axis, there is number of files owned by specific number of users. Let's take two examples for better understanding of this picture. If you create some unique piece of the code, compile it as, for example, myhelloworld.exe, you would be the most probably only one owner of this file. So there are 500 million such a file, all represented by the left blue peak. The other example can be largely spreaded file, like Java.exe. It has many owners, so it belongs to the right side of the graph. It's pretty difficult to deal with different data characteristics in such large volume. Let's try to split them and have slightly different approach to each of them. We named the first part loaners, the files which are owned by less than 1,500 users. We can see 4,000 executions in seconds, so it means 4,000 requests about loaners files. We are interested in this kind of files more, so we require maximum 10 seconds delay accuracy. And we know that there are billion of them. The rest of the files we called top stars. Many users have them. Many users have them at least 1,500. The requests for the information of top stars are about 10 times more than loaners. We don't need so much fresh information about the files. So we found out that 1 hour should do the work for us. And we know that top stars are 1,000 times less in volume. Now we know our data more. And we can split them in kind of separate groups. So we define these 3 groups. On the top left, there are loaners. We can probably store them in NoSQL because the row is not so long and the number of rows can go to billions. The rest, we have some homemade solution we call distributed merger, which is slow in response but can store millions of rows with very long rows, many columns there. And finally, on the top right of the slide, there are some reduced data. We don't need all the information which are in distributed merger. And this part would give us kind of accurate information with quick access. So I will ask Jonathan, and he would talk more about going more deep into the database techniques.
Yeah, hello. So, as we saw, our data is divided into two worlds, each with distinct characteristics and each suggesting different approaches, different technologies. We have these loners, which are huge in number, we're talking about billions of rows, very narrow rows, each row containing just a few columns. For these, we must distribute real-time statistics for all our clients around the world. We may, however, tolerate here short-term inconsistency. We don't mind if after 10 seconds the prevalence of a file will be a few times, larger by a few units. On the other hand, we have the top stars. These are few in number. We're talking about hundreds of thousands, but they generate huge traffic. We're talking about 50,000 requests over the cluster. Now, we could not handle this on a small cluster. We could not support random writes, random reads for such traffic on a small cluster. Here, though, we tolerate delay for the statistic. We do not require immediate update of statistics for these records. So we're dividing these parts of our data set into different technologies. Let's see the considerations behind choosing these technologies. So, according to the CAP theorem, a distributed database system may not guarantee all three of these requirements at the same time. You may pick two of these and left some of the other three. So we had to compound our system from three subcomponents which complete each other, each fulfilling these requirements, which we need them all. So our emphasis was on availability of real-time statistics. We cannot tolerate that our clients would not be receiving response because one machine has failed or it's overloaded or because connection timeouts. Our clients in Brazil would have to be routed to our data center in America and not be routed to Prague or Frankfurt. This would take some 400 milliseconds. So let's see how do we pick the specific technologies. Here we have examples of existing technologies and how they stand in this diagram. We have Dynamo, Cassandra, CouchDB, which are high performance, column-based data stores, which put the emphasis on availability. On the other hand, we have RDBMS system, which persist the data in a consistent form. Down there, we have HBase Big Table, which may scale very well and also support some kind of transactions and atomicity. We hoped we could do that with HBase. We liked very much the elegant programming model and the fact that operation upon a row are atomic. It has, you may inject your code using so-called coprocessors, which are operating on the back end where the data resides. So you may make some kind of transaction using a single trip. It works very well at the start, but as we scaled up the load on the system, we started to have machine failures and response, connection timeout, and so on. So we decided to move to Cassandra. We realized that we simply cannot, we simply must tolerate the inconsistency and put the accent on the emphasis on availability. Cassandra has is very it's extensive tunable options. You may choose your replication strategy, compactation strategy. You may dynamically change the ratio between consistency and replication by choosing the consistency level with which you read or write. Also, it has a distributed cache, which HBase could not give us this. Now, this is very, very useful for us because the clients, one client is writing, and this is being distributed to the memory of another host across the ocean. So Cassandra proved to be very stable, and this is the current choose. Now let's see how the system, the overall system looks like. The system is composed from 3 subsystems, each capturing an edge of this triangle. I was speaking about Cassandra. Cassandra is dealing with the loners. These are the random reads, random writes, immediate response of fresh statistics. Now, what do we do with all the huge traffic generated by the most common files? Yeah, these generate 90% of the traffic or so. Yeah, so these are being streamed into our distributed merger, which is a system implemented by Avast. Its specialization is sequential reads and writes. It's optimized for sequential reads and writes. It's distributed. We may scale it up, add more nodes, partition. As the data is streamed through this system, it's being analyzed and reduced to a scale which is which may be handled by a standard relational database system. So this system is swallowing all this huge data and reducing it to PostgreSQL, where our VirusLab team may analyze it using ad hoc queries, where we may persist it in a consistent form and so on. So now we've seen the components of our system. Let's see how they cooperate together in more detail and how they are implemented.
Okay, so in order to provide you with a better understanding of the application, let me delve more into the guts of the system. So in the following minutes, I'm going to talk about the implementation details of FileRep application. So on this picture, you can see the data flow of the application. There are in basically 2 main loops, which is fed by the requests coming from the clients. These requests are consist of SHA stems along with user IDs. The FileRep front-end server also responds with prevalences, which is the number of files spread around the world. And the outer loop serves for, or it ensures exchange top stars data between the front end and the back end servers. The front end server feeds the back end server with top star requests. And the FileRep backend which is running the merger, the distributed merger mentioned by Jonathan, it performs some analysis that computes the top star prevalences. And these top star prevalences are sent back to the FileRep front-end servers in order to update their caches. On the other hand, the inner loop is responsible for the persistence of the application. The front-end server stores loaner's request to the Cassandra directly, and at the same time it reads loaner's prevalences and returns it back to the clients. The FileRep backend, the merger, reads from the Cassandra some data that is used during the analysis. For example, calculation of top star prevalences. The result of this analysis is written to Postgres, SQL databases, from where it is read by front-end servers during startup, because it contains image of the cache, because something must be loaded in the beginning in order to provide initial response prevalences for top stars. So now let me zoom in to the FileRep front-end server in order to reveal you its structure. The front-end service endpoint is implemented on top of Netty. Now we are experimenting also in Grizzly, and the handler accepts request encoded in Google protocol buffers. The same system or the same format is used for encoding the responses. By the way, we found this system, this framework for encoding the Google protocol buffers very handy, because it is both condensed and also it is legible across various systems. The FileRep handler sends the messages to the daemon, which is right below the handler, and this daemon makes a very important decisions, because it decides whether the incoming request is a request for a top star, or if it is a request for a loaner. If the request bears some data concerning loaners, it goes directly to Cassandra. At the same time, we read data from Cassandra that consists of, for example, prevalence of the loaner being asked. If the request is a top star, the things is becoming more complex. We assume that the prevalence of the top star being under question is already stored in the top star cache. This top star cache is initialized from the SQL database from the Postgres, and it is continuously updated by backend systems, by backend mergers. And at the same time, we send the top star request to the partitioner, whose task is to distribute or to send the top star request to the backend mergers. But the partitioner doesn't send the incoming top star request to the backend. Instead, it pre-merges the request into some kind of chunk or packet, and it sends this packet after some threshold is exceeded. So now let's move on to the backend side. Again, the endpoint of the backend is receiving the chunks I've spoke about before, and these chunks are coming from all front-end servers. But each merger is responsible only for one range of SHA. So there is kind of a partitioning, and every merger has assigned some range of SHA keys. The request handler is again implemented on top of Netty or Grizzly, alternatively. And this handler sends, or it unpacks the chunks or the packets of SHA user ID pairs. And these data go to the local partitioner, whose task is to further partition the data among local mergers, because there can be more mergers than one running on a single instance of the Flutter backend. A merger is a component responsible for merging or combining incoming data with the data that are locally stored. And once a packet or some data appears in a merger's queue, the merger starts copying data from the source disk to the destination disk. And the file which is being copied can be very large. It has about hundreds of gigabytes, I think. And these data are already sorted, and the merger is responsible for combining these sorted big data with the incoming requests. So the result of this merging process is the original data combined or merged with the incoming packets, with the incoming new data. So it's kind of streaming combined with big persistence. So maybe I have to mention that we run these merging processes on separate drives. It is very important because we read sequentially and we write sequentially. So it is very advantageous to read from a different drive than to write. So I think that the normal setup of our service is 8 independent drives. So it means that there are four independent mergers. Each merger is responsible for a certain sub-range of the range of the node, and it's really very fast because we can copy data in the full speed of the drives. But it is also important to say that we can attach so-called merging extensions, or how to say it is, or we call it side effects. These side effects are extensions that can be plugged onto the merging process, onto the copying process, and these extensions can perform some data analysis. One of such analysis is calculation of top star. So this figure shows the schema of calculating top star prevalences as a side effect analysis. The merger feeds this extension with key value pairs where the key is SHA and the value is user ID. The reducer on the picture is responsible just for counting the user IDs belonging to a certain SHA, and which turns out to be the prevalence of the top star represented by the SHA. So the reducer emits SHA prevalence pairs that are going to the distributor. And the distributor is responsible for broadcasting these new key value pairs, these prevalences, to the front-end servers that are used for updating the caches. Also, but we do not send only the bare prevalences. We attach some more information to these key value pairs, and this information is read from Cassandra. Also, the result of the analysis is written to the Postgres, to the SQL database, from where it is read by front-end servers when they are booting. And now let's go back to the front end to close up the loop. Now the receiver is again an endpoint receiving the top star prevalences, and these prevalences are sent by the distributor from the back end, and the front end this front end handler just receives the data from the merger. It unpacks the data, the chunks, and it updates the local top star cache. And whole cycle takes about, I think, 1 hour. So,
on the first diagram, you showed this diamond, but don't you need to access the database to decide whether it's loner or top star?
it's top star. The inner one. You mean the inner loop? Inner loop deals with loners.
Oh, yes. No, I understand your question.
Yes, it doesn't.
It does.
It's read from cache. It is because the top star cache, the ellipse, is fed from the back end. So we regularly update this top star cache from the back end. And sorry? Yes, it's in memory. It's in memory cache. This is a very interesting question, and it is under analysis now because this is a very fresh system, and now we are experimenting with observing the dynamics of the system I am describing now. But it's very difficult to say now. But it may be very quick, and also it may be very slow. No, we were experimenting with Hadoop. Because first we used HBase as a NoSQL storage, and also we tried to write some Hadoop jobs, and but now we do not use it. Or you not use it? Do you use it?
Just for other projects.
For other projects, but we used to use it, but now we do not use it anymore. But maybe in the future. The cache, no, it is just a hash map, because we do not need to distribute the data, because there is the distributor on the back end who broadcasts the data to the caches. There are 500,000 rows, so 500,000 entries, so 500,000 top stars. Just in one JVM. It doesn't take too much of memory. It's about, I don't know, 1 gigabyte or 2 gigabytes. It's only, maybe Pavel should answer this question, because he's a guy, the database guy.
Yeah, we played with different kind of databases, and we found out that Postgres we can tune. Well, okay, we can yeah. This is a good question. We can also put the top stars data into the Cassandra, but we are also using the Postgres for doing some analytic stuff, to doing the query, and then using SQL as the selects on them. It is good, yeah, but it cannot contain the whole row of data. That's why it's reduced. It's reduced enough so we can do the analysis and selects on top of them. Yeah.
Okay. So in the end of this section, I would like to mention some implementation details. So first of all, I would like to mention something about the request handlers. Because I've already said that we implement these request handlers on top of Netty or Grizzly, but we do not write it directly on Tepi or Netty or Grizzly. Instead, we have developed our internal platform called Reactor, and there is an abstraction of the NIO core, and there are two implementations of this NIO core. One is written in Grizzly, and the other is written in Netty. So it is exchangeable. We can switch the core according to our requirements. And there is one important point regarding this NIO asynchronous processing, or synchronous or asynchronous, because it allows us to choose dynamically whether the incoming requests are to be processed asynchronously or synchronously. Because, for example, if we read top stars from the cache, it's an in-memory cache. We can we should process or execute the request synchronously. So it means to process it in the same thread as the thread which receives the events. On the other side, if we, for example, read some data from Cassandra or write to Cassandra or to Postgres, we have to perform the operation asynchronously. So we just indicate in some callback method that this request should be executed either asynchronously or synchronously. Also, one note regarding Cassandra, because we use Cassandra Connection Pool, which is an open source library that you can download from the URL mentioned on the bottom. We found this Cassandra Connection Pool very flexible and robust, and it also provides us with different failover policies, and it's based on Tomcat JDBC pool. And last but not least, I have to mention so-called coroutines. These coroutines allow you to suspend a method execution and return to the caller. The caller continues in its operation, and it can decide later on to return back the execution to the point where the execution in the method was suspended. It resembles kind of to a multi-threading, however, running in a single thread. We use this technology in reducers, allowing us to transform the push event system to pull one and use loops instead of callbacks. So it's very convenient for us because we do not have to write some callbacks, because all the system I've been describing is event-driven. So there are events being emitted from the merger, and there are various extensions that are receiving the events. So in order to write some analysis procedure, this procedure should write many callbacks on at least one, and this callback would receive the events, but sometimes it is necessary to remember some context for this processing. So in this event-driven programming, it is kind of difficult to preserve the context. But if you write, for example, if we write the code kind of like a reducer in a map-reduce paradigm, it's much more easier and convenient to preserve the context, because you use iterators and you just loop through these iterators, and you can preserve the state on the local stack. So these coroutines allows us to write this map-reduce code, and it behaves as if it were a traditional map-reduce thing, but in the background it is an event-driven system. So now I would like to hand over the microphone to Pavel, and he is going to say something about the infrastructure.
So, how does the deployment look like in the reality in the end? So, we have two geographically different locations. They are on the other side of the globe. We are now adding the third location. So on the picture you can see left and right. The requests from clients are differentiated based on DNS response, so we know where the clients are, and we are sending them to appropriate part of the world. In each location, there are 8 Cassandra nodes, which creates the Geo Cluster. Then, if you can see, the top stars request can be answered directly from the node's cache, so it's in memory cache. And if it is not in the cache, it's not top star, and the Cassandra is asked for loaners data. So, for doing operations with the top stars, there are distributed merger and PostgreSQL, but it has the delay with the accuracy. So it's the blue requests. Okay, that's about it. Thanks for listening. Any questions you have? Okay, the question is how many key spaces we have and column families. Yeah, we have 2 key spaces, and each has 1 column family. The 1 key space is just for storing data, and then we can do some dump of Cassandra and then do analytics for that. The other key space is the actual one which is quick for reads and writes.
Also, this other one is the one which is loaded into Cassandra cache. We have 1 key space which is we set up row caching, so it is actually also a distributed cache. This is the one that gives the answers, the real answers. The other one is like for persisting huge data. So you never at one point in time decide using the software. No transactions, no locking. We're doing one write, 1 read, and 1 write, right, per request. Otherwise, we would have been risking race conditioning.
Any other question? Yeah. Okay, the question is what happened if the data center split? Yeah, this is the information then after. If the data centers are actually split, then the data are not propagated around the whole world. So it actually like 2 pieces. Half of the globe knows only about the files on the half of the globe. But when it gets connected again, then it's nature of the Cassandra, it's being updated, or we can repair the nodes or something like that. And also it gets updated the data from the distributed merger. So for some time there would be split system, but it will converge to the stable status later on. Yeah, if you let it split like for 1 day, then you can see that there are different top stars on different location, yeah, and different files, but when it gets connected, it will be balanced again. Thank you.